Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 1 on integers and rational numbers. So Unit 9 is really an exploration of a variety of things including square roots and what are known as irrational numbers. But before we get into irrational numbers, which are a little bit of a mystery, what we want to do is we want to review some things that you probably already know about both integers and what are known as rational numbers. So let's jump right into them. Now, whole numbers versus integers. Numbers, at their core, measure how much of something exists. When we count objects, right, 0, 1, 2, 3, 4, it's enough to only have whole numbers. But when we measure quantities like weight or volume, we need fractional amounts. Over time, people have either invented or discovered different types of numbers, all right? So we're going to be talking about a few of those today. And let's jump right into exercise number 1. Two of the most basic types of numbers are the whole numbers and the integers. Give organized lists of both. All right, so whole numbers are definitely the first numbers that you ever learn about, ever, right? And it's simple enough. In fact, let's just do these together. An organized list of whole numbers, we're going to write these out in roster form, set form, is 0, 1, 2, 3, and then we'll put a ... to indicate that they go on forever. Right? There's an infinite number of whole numbers, and again, this is where you start, right? And it totally makes sense because even as a young child, right, you're already thinking, oh, I've got 3 cookies, I've got 2 of my best friends coming over. All of those are counts, in which case we need these whole numbers. Now for letter B, we've got the integers, and it's almost difficult to describe the integers because the integers and the whole numbers look a lot alike. The difference is that the integers also have negative whole numbers involved, all right? And again, some people would say, well, you can't say negative whole numbers because whole numbers are by definition either 0 or positive, right? But the integers, right, are basically numbers that don't have any fractional part. Now, they extend forever in 2 directions, which means that I sort of start my list with a ... and then I end it with a ... right? So in other words, right, I've got, the numbers going this way and I've got the numbers going this way. None of them have fractional parts, right? But they could be both positive and negative. We oftentimes will use integers even when we're just talking about whole numbers. And we really want to just think about the integers as being numbers that do not have fractional parts to them. All right, that being said, let's keep talking about these. Now, the closed nature of integers. Integers behave nicely when it comes to the operations of addition, subtraction, and multiplication. And this is what is known as being closed under these operations. Now, what does it mean when they behave nicely? Well, let's take a look at exercise number 2. Finish each sentence and give an example. All right. Now, what's kind of great about this is that every one of these is going to have the same word in it. Letter A, an integer added to an integer gives an integer. That's what I mean by integers behave nicely. When I take an integer and I add an integer to it, what I get as an answer is an integer. The more I say that word, the funnier it sounds. All right. And again, what's great is you can choose basically any example you want. Grab a couple integers, add them together, and you're going to have an integer. Now, we could just stick with whole numbers here and keep working with those, but I'd like to involve some negatives. So, maybe a good example would be, let's say, -8 plus 5 is equal to -3, okay? There is no point in time when I'm going to add 2 integers together and get a number that is not an integer. And likewise for letter B and letter C, an integer subtracted from an integer gives an integer. All right? There's no way to subtract 2 integers and get a number that has a fractional portion to it. So you could, again, take basically any example you want. You could say, let's say 7 minus -2 is going to be equal to +9, right? Again, pick 2 integers, subtract them, you should get a number that's also an integer. And finally, an integer multiplied by an integer gives me an integer. I don't have to invent a new number, right? So maybe I've got 5 times -4 is equal to -20. right? So in other words, if the only numbers I ever had were integers, right, and that was it, then I could do all the addition, subtraction, and multiplication I wanted, and I wouldn't have to invent a new type of number. Now, just to make sure that you understand this idea of a system being closed, right, or a set of numbers being closed for a particular operation, let's take a look at exercise number 3. Given the whole numbers, just the whole numbers, i.e. 0, 1, 2, 3, 4, etc., explain why we cannot say that the set is closed under subtraction. All right, now side note, the whole numbers, 0, 1, 2, 3, 4, etc., are closed under both addition and multiplication. In other words, a whole number plus a whole number gives me a whole number, and a whole number times a whole number gives me a whole number. But I claim that the set of whole numbers is not closed under subtraction. Think about why that is. Pause the video now and play around with it for a little bit. All right, so for a system to be closed, you don't have to invent a new number in order to do an operation. And yet, if I did something like 2 minus 7, I would get negative 5, right? And this is not a whole number, right? And it's interesting, except of course early on, right, when all you knew were the whole numbers, right, well, that was all you knew, then your teacher might say to you, well, you can't do 2 minus 7, right? Or you might have said 2 minus 7 is equal to 5, right, kind of treating subtraction the way that you'd treat addition. It's commutative. It's not, by the way. But you know, we didn't really have to have negative numbers because anytime we ever did a subtraction problem, it was always a larger number minus a smaller number, in which case you'd still get a whole number. But as soon as you do a smaller number minus a larger whole number, you get a number that is no longer a whole number. Still an integer, right? So subtraction is definitely closed, you know, for the integers, but not for the whole numbers. Now, division of whole numbers, notice that one we've kind of left off. Division of whole numbers and integers gives rise to a new type of number altogether, one that has haunted students since it was first invented. So let's take a look at exercise number 4 to make sure we understand what I'm talking about here. Give an example of a division problem involving whole numbers that does not result in another whole number. What kind of number does result from this division? All right, so pause the video now and pick 2 whole numbers that when you divide one of them by the other one, you don't get, and I shouldn't say just whole numbers, you could, well, actually it does say whole numbers, but we could involve the integers as well, but just stick with the positive ones, right? Pick two whole numbers that when you divide them doesn't give you a whole number again. Pause the video now. Well, there's tons of examples. In fact, there's more examples of dividing 2 whole numbers to get a non-whole number than there is dividing 2 whole numbers that does give you a whole number, right? So just pick anything. Like, for instance, I like something like 2 divided by 4, right? I can always write any division problem as a fraction, and 2 divided by 4 is 1/2, right? That is definitely not a whole number. Okay, and in fact, the type of number that does result is a fraction, right? Now we're going to give those fancier names in just a moment, but, right, when I take a whole number and divide it by another whole number and don't get a whole number as a result, what I'm getting is a number that at least has a fractional part. Even if you do something like dividing a larger whole number by a smaller whole number, 8/3 is still a fraction, right? It's 2 and 2/3, okay? No longer a whole number. So division is where all of a sudden, oh, you know, if I've got 8 cookies and I want to divide it amongst 3 friends, well, each friend doesn't get a whole number of cookies. They get 2 plus another 2/3 of a cookie, right? And maybe I just gave away number 5, but let's talk about number 5. Give an example of a real-world situation, not involving cookies and friends, where we would need fractions in order to measure some quantity. Explain why fractions are needed. All right, now there are tons and tons and tons of examples in the real world where fractions are necessary, right? They're very, very necessary. Pause the video now and see if you can think of any situation where you've got to have a fractional quantity in order to measure something. Pause the video now. Well, again, there's tons of examples. They come from things like construction to weighing yourself to, let's say, cooking. Cooking is a great example, right? Like in cooking, we often measure a fraction of a cup or teaspoon or gallon, etc., right? And that always happens when we have some set quantity that represents the number 1. You know, for instance, 1 gallon, or 1 foot, or 1 pound, right? And then we try to measure something in terms of that 1 gallon, or 1 foot, or 1 pound, but it isn't an integer or whole number multiple of that, right? And therefore we then have to have a fraction. So when I, decide to make some muffins or something like that, and it calls for 2.5 cups of flour, I need to have fractions, otherwise there's no way I'd either have to have 2 cups of flour or 3 cups of flour. I couldn't talk about 2.5 cups of flour, right? So we oftentimes have to use a fraction when we do things like cooking or measurement of anything that isn't a count, right? When we count things, how many dogs are in the house? How many internet-enabled devices do I own? How many cars are in the parking lot? Those are all counts. On the other hand, if I said, well, how tall is that person? Or, how much flour do I need for that recipe or whatnot? That's more of a measurement, and I could easily have quantities, right, that don't fit into a whole number quantity, a count. Now, this gets us into a very important idea, the rational numbers. When we combine the positive and negative fractions with the integers, we get a set of numbers known as the rational numbers. The rational numbers. So let's kind of take a look at the technical definition of what a rational number is, all right? A rational number is any number that can be written as the ratio of 2 integers. In other words, it can be written as a fraction in the form a over b, where both a and b are integers and could be positive or negative. All right? So if you can write a number as a fraction where both the numerator and denominator of the fraction are integers, then that is what's known as a rational number. Okay? And again, rational literally comes from the fact that it is a ratio of 2 integers. All right, so let's take a look at some rational numbers. Exercise number 6. Each of the following numbers is a rational number. Place it in the form a over b, where both a and b are integers. So one of the interesting things is that integers, and we've got 2 integers hanging out in this problem set, all integers are also rational numbers because they are the ratio of that number to the number 1. Right? So in other words, I can write 5 as a rational number if I express it as 5 over 1. Literally, 5 is the ratio of 5 to 1. So, hey, it's a rational number, right? As long as it can be written as a fraction where the top and the bottom are both integers, it's a rational number. Now, 7 1/2, see if you can remember a little bit from middle school on how to write that as in the form of a over b. Pause the video now. All right, well, 7 represents 14 halves. With another 1/2, that gives me a total of 15 halves, and there's our rational number, right? 7 1/2 is the ratio of 15 to 2. 15 to 2. Now, we could also have these decimals in terms of rational numbers. The number 0.5, that one's probably pretty easy. See if you can write that one as a rational number. Now, the rational number for 0.5, and really for any rational number, is not unique. Okay, it's not unique. In fact, this is 5/10. So maybe the easiest way to write this as a rational number is literally 5/10. Right? There it is. It's the ratio of 5 to 10. If you said to yourself, well, but I looked at 0.5 and immediately said, that's the number 1/2, great, absolutely, right? So the way that we write a rational number is never unique, okay? We could actually write 5/1 as 10/2. 15/2 we could write as 45/6, all right? And of course, 5/10, if we really wanted to get crazy, we could write that in an infinite number of ways, 10/20ths, 2/4, etc., etc. All right, pause the video now and see if you can write letter D and letter E as rational numbers. All right, well, letter D is basically the same as letter A. You could write this one as -3/1 if you really wanted to. You could write it as 3/-1. That would be fine as well. Doesn't really matter. Both of those are fine, and there's a myriad of other ways to do it as well. Now here, I've got 0.93, which is 93/100ths, right? There it is. There's your rational number, 93/100ths. So that's all rational numbers are. Right? Now, they are the numbers that you use the vast majority of times, and we will eventually in this unit be talking about irrational numbers. All right, those will come up in the next few lessons. But for right now, let's just stick with these rational numbers, numbers that can be written in the form of a ratio of two integers. Now, all rational numbers have a decimal representation, right? So let's talk about the rational numbers written as decimals. All rational numbers have decimal representations or versions whose decimals either terminate or repeat. And by terminating, of course, we mean something like 0.5. That terminates. Or 0.25. That terminates. Repeating would be something like 0.111111111 that goes on forever. All right, so let's take a look in exercise 7 at some very common fractions that hopefully you already know the decimal representations for. Let's take a look. Write down the decimal version of each of the following common fractions. Do so without your calculator. Use the repeating decimal bar as necessary. All right, well, let's see what you can remember from middle school math. You've been seeing this since 6th grade. So let's see if you can fill in the decimal version of 1/4, 1/3, 1/5, and 3/4. All of these are very common. We, of course, just saw the decimal version of 1/2, that's 0.5. So pause the video now and see if you can fill the rest of these in. Now, you might say to yourself, well, hey, I got my calculator. I can just do it on my calculator. Yes, true, but there are certain fractions that you should just know the decimal version of. For instance, 1/4, right? You should know that that is 0.25. That just terminates. 1/3, on the other hand, is a nice repeating decimal. That's 0.3, 3333333 forever. So that's 0.3 with the repeating decimal bar. 1/5 is 0.2, that terminates, and 3/4 is 0.75. I would hope that both letter A and letter D you're very comfortable with simply from the perspective of money, right? If I said how many pennies are in 1/4, you would hopefully say 25, and of course, how many pennies are in $1, that would be 100, so that should make sense, and of course, 3/4 the same way. Now, let's take a look at exercise number 8, where we will bring out our calculator in a moment. Using your calculator, write the decimal form for each of the following common fractions. Use the repeating decimal bar as necessary. All right, so my claim is that those ones in exercise 7, there's no question you should know their decimal versions just like that. On the other hand, you might not know the decimal version for 1/8, 1/9, 1/6, 5/12, etc. So you should be able to use your calculator. Now let me break the calculator out and let's talk about calculator use on something like this. Now, one thing I would advise right away, on many calculators, the number of decimal places the calculator shows you is somehow fixed, right? And you can tell it how many decimal places to show. On my TI Inspire, I believe that the basic version only was showing me 4 decimal places, which is not great because then you might think that, the fraction just terminates. So a little bit of heads up, at least on the TI Inspire. Okay, now this is going to be different depending on the calculators. I can set the number of decimals that my calculator shows me by going into my settings. All right, on the TI Inspire, it's called the document settings, and literally the first thing is what's called display digits. Right now, my calculator is showing me what's called float 5, okay? What that means is if I put something like 1/3 in, now by the way, if I just hit 1 divided by 3 and I hit enter, the calculator is just gonna do this. 1/3, yes, 1 divided by 3 is 1 divided by 3. If I wanted to actually show me the decimal version, I have to put in 1 divided by 3, and then what I do is I hit the control button and the enter button, and it turns it into a decimal. But notice, it gives me 5 3s, right? 0.33333, right? It gave me 5 decimal places because this is what's called a float 5, meaning that it will give you 5 decimal places if it needs to. On the other hand, if I did something like 1 divided by 2, or 1/2, and I hit enter, it does 0.5. It doesn't give me 5 decimal places because it doesn't need to. The thing terminates. Now, I want it to give me as many decimal places as it can right now. So I'm going to go back into my document. I'm going to go into my settings. I'm going to go into my document settings. Wow, that was a lot. And instead of float 5, I'm going to go all the way down and do float 12, okay? That will give me 12 decimals if it keeps going out that far, all right? So now I'm going to hit OK. And now if I did 1 divided by 3 and hit enter, I would get 12 3s, right? And that's probably enough to let me know that, yeah, this is probably like a repeating decimal. Okay, that being said, let me just minimize this real quick, right? I want 1/8, 1/9, 1/6, and 5/12. All you have to do is put those in as division problems and write down all the decimals that your calculator sees, unless you think that it's repeating, in which case use the repeating decimal bar. Pause the video now and see if you can write down the decimal versions of those 4 fractions. 2 of them are going to have repeating decimals and 2 of them will terminate. All right, well, let's bring the calculator back up real quick and let's take a look at 1/8. Actually, let me just do this real quick and clear out my screen. So if I do 1/8, and again, I do Control Enter, I get 0.125. Now I know it terminates because if it didn't terminate, it would show me, right, I think, what was it, float 12, right? It would show me 12 digits, right? So I've got 0.125. All right. Now 1/9 is kind of cool because it doesn't terminate, it repeats. It's one of the most famous repeating decimals. When I do 1/9, I get 0.1 repeated, 0.111111111, which is really awesome. And when I want to represent it, I will just write it as 0.1 with that repeating decimal bar. Now, of course, many times in the real world, what we need to do is we actually just end up like rounding this in some way that the problem suggests or that is a rule or something like that. Let's take a look at 1/6 real quick. It's also going to be one that repeats. If I do 1/6 and I do enter, I get 0.1666666. Now, notice, right, at the end, it's put a 7. Now, it's not that this decimal terminates right there, right? It's that the calculator says, well, these are all the digits I'm going to show you, so I'm going to round that last one off, okay? That's a rounding thing. This is 0.16 with the 6 repeating, but not the 1. Be careful about that, right? So if I want to represent this, I'm going to represent it as 0.16 with the repeating decimal bar only over the 6. All right, and finally, 5/12. So let's take a look at that one. I believe that that one terminates. Let's take a look. Oh, it doesn't. No, I lied to you. It's 0.4166666666, right? So the 0.4 and the 1 don't repeat, but the 6 does. That was my bad. 0.416 with the 6 repeating. All right, let's go back into our full screen and advance. Now, fractions whose decimals terminate are kind of boring, in my opinion. Now, they're useful, and probably some of the most important fractions out there, things like 1/2, 1/4, 3/4, right? 5/8. All of those terminate, right? And they're very important fractions. But let's take a look in our last exercise at ones that can have really fascinating patterns when they repeat. Let's take a look at exercise number 9. Write the decimal representation for each of the following rational numbers. Each will require the repeating decimal bar. Okay, so this time, there's no question, every one of these things has the repeating decimal bar in it. But I've kind of arranged these so that they make really kind of cool patterns. Any fraction or any decimal that has a repeating pattern to it can be written as a rational number. So now I'd like you to pause the video. I'd like you to work out what you think are the correct ones, using your calculator, absolutely, the correct repeating patterns on each one of those fractions. Pause the video now and take a moment. All right, let's take a look at some cool patterns. 7/33, right? No big deal. 7 divided by 33. Cool, cool. Let's bring this thing up. I'm gonna clear this out again. Let's do 7 divided by 33. And we get 0.212121212121, etc., right? So we literally have 0.21 with the 21 repeating. Back and forth, back and forth. Kind of cool. So this is 0.21 with the 21 repeating. All right, let's take a look at 25/27. 25 divided by 27. Enter. And I get 0.925, 925, 925, 925, etc. Again, make sure you realize that final 6 there is not the fact that the decimal is terminating, it's the fact that it rounded that last one. So this is 0.925 repeated, 0.925. With all 3 of those repeating again and again and again. All right, let's take a look at 23/101. 23 divided by 101 gives me 0.2277, 2277, 2277, etc., right? So this is actually one that has 4 digits that repeat, and then it's got like 2 that repeat, 2 that repeat, another 2 that repeat, another 2 that repeat, etc. So 0.2277 repeated. A little bit tricky there, but there it is. And now finally, 100 divided by 303. Let's bring this thing up. 100 divided by 303. Oh, made the classic mistake there. There it is. 0.3300330033, etc. All right. You're going to learn a little trick in the homework on how to create these kind of repeating decimal patterns. Not that that's of very much use, but it is kind of cool to see that sort of like way that these things pan out. So let's put this one down, 0.3300. So this is 0.3300 repeated. Like the last one, it's got 4 different digits that repeat. Okay. Let's finish this lesson up. So the main purpose today wasn't to look at cool repeating decimal patterns, although that was a bonus. The big point today was really understanding number systems. Understanding that sometimes, you get numbers that, a system that, hey, when you add a couple integers together, you get an integer. Subtract, you get an integer, etc. Then all of a sudden division comes along and it's like, wow, what is 13 divided by 3? Well, that's not an integer anymore, right? So you have to invent a new type of number, and those types of numbers we call fractions, or in a broader category, rational numbers. And rational numbers are really key. In the real world of math, right, and science, even though irrational numbers come up, no question about it, almost always what we are ultimately using in calculations are rational numbers. Ratios of 2 integers, okay? And we did review the fact that those ratios of 2 integers have decimal patterns that either terminate, like 0.5, or repeat, like 0.121212, etc. All right. Anyway, we're going to be contrasting rational numbers with irrational numbers in just a few lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.